So this video begins our first of a series of 4 on conjugate priors, and in this one we'll look at the simplest of the conjugate priors, the beta-binomial. We will first review what it means to be a conjugate prior, and then we'll look at the specific case of the beta-binomial. So from the last video lecture we discussed the notion of conjugate priors, and in that we said that obviously from Bayes' rule, we know we derive a posterior from the product of the likelihood with the prior divided by the likelihood of the evidence. Okay, so it turns out that for conjugate priors, we have the case where the prior distribution, the family that the prior is from, is exactly the same as that of the posterior. So the prior distribution could be, in this case, from a beta, and the posterior will also be from a beta. And that works when the likelihood function has a specific form, and in this case that form is a binomial. So let's look directly at the case of a beta-binomial then. So for the beta-binomial conjugate family, we start out with the distribution of the likelihood function, which is the distribution of the data. And remember that in a binomial, the data consists of a sequence of Bernoulli trials. That's a sequence of 0, 1 trials, because our random variable is 0 or 1. So in this case, we've expressed it as n trials. X is the vector of Bernoulli trials. X1 then would be either a 0, 1, X2 would be a 0, 1, and so forth, all the way up to Xn. Okay, the likelihood of getting a 1 in for this particular case, we're designating as theta. And so theta is the probability then that in that Bernoulli trial I get a 1. So if I look at all n of those cases, then the likelihood function is proportional to the product of theta to the xi times 1 minus theta to the 1 minus xi. And what this means is quite simply that if on our first trial, let's say x1, we roll a 1, or we get a 1 in our Bernoulli outcome, then we have theta to the 1, which is the value of x1, okay, and we have 1 minus theta to 1 minus 1, which is 0. So we're left with just theta to the 1, or just theta, which is the probability of getting a 1 in that trial. And you could see that works if we have a 0 on one of our trials. The theta to the x will in that case be just a 1 because the x will be 0, and 1 minus 0 will be 1, so we'll end up with 1 minus theta, or the probability of getting a 0. And the product of all of those then represents the kernel of the binomial, which is the probability of getting that sequence. Now, the specific sequence is given by the part that we've left out, that factorial part in front of the binomial. But we really don't care about that part. All we care about is this kernel part, which gives us the functional form of the distribution. The beta prior, if you recall, takes each one of those individual probabilities. So now we're looking at the probability that theta, in this case, takes on a particular value, let's say 0.5 or 0.6, okay? We're saying that actually has a beta distribution. So the likelihood of seeing a 0.5 or a 0.6 then is given by the density function described by the beta prior. And again, we're just showing the kernel part of that density. We're leaving out the beta function that's in front of it that normalizes it, and just focusing in on the part that really matters to us, which is this kernel part of that density function. Theta to the alpha minus 1, the first parameter in the beta is alpha, and 1 minus theta to the beta minus 1, again, the second parameter is beta. Okay, so if we have a binomial likelihood function and we have a beta prior, then it turns out we use Bayes' rule, and we can easily see that we have a beta posterior. Hence, we have this conjugate family, beta binomial, gives us a beta posterior, okay? And that's a nice feature about this particular analysis, known as conjugate analysis, is that we quickly derive a posterior distribution. And the posterior distribution has a nice closed form solution to it. We can see this easily if we do the algebra, since the likelihood function is the product of these thetas to the xi. That's the same thing as theta to the summation of the xi's. And now we multiply that by theta to the alpha minus 1. So we just add alpha minus 1 in that exponent, and we get theta to the summation of the xi's plus alpha minus 1. In a similar fashion, we have 1 minus theta to the n minus the summation of xi, which is that product form that we see in the likelihood, and we have 1 minus theta to the beta minus 1, which is the form we have in the prior, multiplied together, which puts 1 minus theta to the n minus the summation of the xi's plus beta minus 1. And that forms the kernel of our posterior distribution. The normalizing function in this case is given by what we show as C1, which is just the normalizing terms that make this into a density function. Okay, with this posterior distribution now, we can easily get the posterior mean because we know the formula for the mean of a beta, and that's simply now, in this case, going to be the summation of the xi's plus alpha over n plus alpha plus beta. And we can rewrite that as a weighted sum, where C2 is the weighting, and that weighting is shown as alpha plus beta over n plus alpha plus beta. So it's a weighting of the prior mean, alpha over alpha plus beta, plus a weight times the average, the sample average. And notice that given that weighting, that C2 weighting, as n gets large, C2 gets very small, which means that our mean, our posterior mean, then is going to not have very much of the prior mean in it. In fact, it's going to be almost entirely the sample average. So as n gets large, we're going to converge to the sample average. We can also look at the posterior variance, and in this case, look at the denominator, and you'll see that as n gets large, this term for the variance is getting very, very small, and in fact, it's going to 0. So if we look then, the limiting results are as we get more and more samples, that the posterior mean is going to converge to the average of the samples, and the posterior variance is going to converge to 0. When we look at prediction, we're asking the question, suppose we get a new sample point. What will we predict for the value for the new sample point? And we can easily find this, and the way we do it is by using that conditioning argument that we made several lectures ago, where we condition on another random variable. In this case, the random variable we're going to condition on is the value theta. And it's a convenient one to condition on because we know the distribution now. We know the posterior for theta, given that we observe the data. So we just use our conditioning argument, and that then is going to be the integral of the likelihood of observing this new value, okay, given the value of theta and given the data that we've observed up until now, times the posterior distribution for theta, and we just integrate that over all values of theta. And if we do that, then we can easily find the value, for instance, the density function for a value of 1 in this new Bernoulli trial that we have that we want to estimate, okay, is just going to be given by the posterior mean, and the posterior mean is as shown. So it's a very simple thing then for us to predict new values given this conjugate analysis with a beta-binomial conjugate family. Let's look at some examples really fast of how this is used, what it looks like. These are examples of beta distributions. We've talked about this before. The beta distribution can take on a variety of different shapes, from a bathtub type shape to unimodals to highly skewed distributions. And here's other examples with different values for alpha and beta parameters, very much unimodal. Okay, so if we look at an example of how this works, here is a problem in which we've got a known theta value, a known probability for our Bernoulli trials of about 0.38. And we start with three different prior distributions. One is a beta 1,1, which is basically the flat blue distribution that's shown there. Another one is a beta 1,1, which is, beta 5,5, which is the distribution that's shown in the middle, the orange distribution. And the final one is a beta 1,6, which is a highly skewed distribution. So the beta 1,1 tells us we have no idea where the value of theta is. The beta 5,5 says we've got a pretty good idea and we think it's right around 0.5. And the beta 1,6 says we think we have a good idea and we think it's very low, that it's likely to be a very small value for theta. Okay, and you can see what happens as we get more and more trials. And I've considered this to be flips of a coin. So in other words, in our first flip of a coin, or first two flips, if we get one flip, we get one head. You see what happens. These distributions move very little. But the posterior distributions, because now we're plotting the posterior based upon the priors that we had in that very top plot. And you can see that as we get more and more trials, 2 trials with observed one head, and then 3 trials with one head, you can see that these posterior distributions are converging a little bit. And as we get more and more trials, all the way up to 50 trials, you can see that they're converging pretty close to the true value. And by the time we get to 150 trials, they've converged right around it. And it didn't matter really where the prior distribution was initially. The initial guess for those prior distributions, you can see that they change a little bit, and the initial guess is moving in the direction where the one where we thought that there was a bias in the coin, it was a little bit low, which was that beta 1,6, moves a little bit more quickly to recognizing the value of the true value. Although the one that also moves quickly is the uninformed one, the 1,1 beta. But in the end, they all move to the true, to where the true value of theta is, and we can see that they all give you a nice distribution around the true value.